in order for a reaction to occur, the particles of the reactants have to collide with one another. But not all collisions are going to result in a reaction. Similar to how your airbag in a car won't necessarily deploy if you just bump into somebody else's bumper. There may not be enough energy there to start the reaction of the airbag deployment. But if you're moving a bit faster, then that increased kinetic energy is going to provide sufficient energy to get the chemical reaction of the airbag mechanism started. So the collision has to have a certain amount of energy, must have sufficient energy in order for the reaction to occur. And so this amount of energy is referred to as activation energy. Now, the lower the activation energy requirement is, that translates to the easier it would be for a reaction to get started on its own. And so when we talk about spontaneous reactions, or reactions that appear to occur on their own, they still have this activation energy requirement, it's just that it happens to be a very small requirement. Graphically, if we graph the energy of a reaction over the course of the time of the total reaction, we can see what relative energy our reactants are at and the products that we're going to form. And between them, we see the progression of the reaction in terms of energy. And all reactions, whether they're endothermic or exothermic, will have the same appearance. And you'll have this hill that has to be climbed first before your particles, your atoms, can proceed to and form the products. And so this energy difference is known as the activation energy, represented as E sub A. Now, if you have particles colliding and they are anywhere on the left-hand side of that hill, when they collide, they have a total energy that is somewhere beneath the level that summit is at. Those collisions are not going to be effective. It's only collisions that would exceed that activation energy height that would potentially result in the formation of products. Now, the difference in energy between the reactants and the products themselves, that is what we refer to as the heat of reaction. It's also known as enthalpy, capital H. Previously we've talked about heat of reaction and defined it with the variable Q, or Q sub R. But enthalpy is the same thing. And so if we look at the enthalpy for a reaction, if we get an enthalpy that is less than 0, meaning that our products are at a lower energy than our reactants are, that means we have an exothermic reaction. To find the enthalpy, you take energy of products minus energy of reactants. If the products are at a lower energy, that's going to result in a negative delta H value, and thus it would correspond to an exothermic reaction. If we have a situation like is diagrammed in the chart you see here, where the products are at a higher energy than the reactants, that's going to give you a positive delta H value. And what this means is we have to add energy to the system to get the atoms from the reactant state and arrangement to the product state. So we are adding energy to the reaction, and therefore it's an endothermic reaction.